Okay, let's get going. We want to start looking at the example that we were looking at. And here we go. So what we want to do here is that I want to use this four-step process. Do you have to do this four-step process? Of course not. But you better hit all of these processes, all these steps in some shape or form. I don't care how you do it, as long as you do it right, right? So I typically, the way I set it up is that I solve for the initial voltage of the cap before the switch is thrown. After this thrown, then we solve for the Thevenin parameters. There's 3 of them. VOC, RTH, and then 1 over the time constant, not the time constant. The only time we care about the time constant is when we have to do the plotting. And then once I have my circuit, which is in Thevenin form, I then use the Thevenin solution to write down. Then typically I go back and I solve the circuit problem. Okay. And remember, these circuits cannot use mesh or node. So here we go. Here's my circuit. And what I'm going to do here is that I'm going to go through the Thevenin steps. And my Thevenin steps here says I'm going to determine VC at 0 minus. So what does that mean? That means that the 6 ohm resistor is not included. And then I have 2 resistors in series with the cap. I replace the cap with an open. And I could see here that there's no current in the circuit. So the 3 and the 6 are dead. So clearly VC of 0 minus is 3 volts. Now I know what the initial voltage is. So now I go to step 2. The switch is thrown now. That means the switch is closed. I now include the 6 ohm into the circuit. And here's what my circuit is right here. So what I need to do here is that I need at t equal to 0 plus, I determine the Thevenin parameters, which are 3, VOC, RTH, and 1 over tau. Here I go. To determine VOC, I remove the cap. There's the cap. That makes that this 6 ohm resistor is a dead resistor. So therefore, I could see that the voltage across the 6 ohm resistor is the same as VOC. So then I use voltage divider rule to get the voltage across the 6 ohm. So I end up getting 2 volts. Now I need to go determine RTH. So how do I determine RTH? Well, I short out the voltage source. Why? Because this is a constant source. Could I have done I short circuit? Yes. But in this case, because it's a constant source, I'm going to use that technique, that method 1 from the Thevenin circuit. So what I see here, I can see here is that the 6 is in series with the 3 and 6 in parallel. So therefore, R Thevenin is 6 plus 6 parallel to 3, which is of course 2. So that gives me 8 ohm resistor. So now I need my time constant. Okay, so I'm going to go determine one over tau. So what I do here is that I know that tau is RTH times C. Now, what do I know? Well, we just calculated that this was 1 ohm, and the capacitor is 0.05 farads. And when I multiply these, I get 0.4 seconds. This tells me then that 1 over tau is then going to be 0.4 over 1, and this will be 2.5 hertz, and that's 1 over tau. So now I have my tau value, 1 over tau that is. So then what I'm going to go to is I'm going to go to step 2, or step 3, excuse me. So what I'm going to do now is that I'm going to put VC of t, I'm going to put the voltage into solution form. Okay, so let's go do that. So I have all my details now. So then I know that VC of t is what? VOC plus VC of 0 minus VOC e to the minus t over tau. So then I know that VOC is 2, and then I'm going to get 3 minus 2 e to the minus 2.5 t. So when I look at the solution here, this means that this is 2 plus e to the minus 2.5 t, and this is VC. Now, to put it in a little, I don't have to do this, but I'm going to try to make it a little bit easier for plotting. So the way I'm going to write this then is that I'm going to write like this. So my solution then is VC of t. We know that this is the important value like this, and this is for t greater than 0. And then it's 3 volts for t less than 0. And I'm going to say that this is the solution. Now note, I didn't have to write it this way. I wrote it this way to make sense of what it means. So now what I want to do here is that I want to interpret. So what does this mean? So if I look at the solution, so the first thing that I want to do here is that I want to look at the solution. The solution tells us that VC of t is 2 plus e to the minus 2.5 t. Of course, volts. So the first thing that's important to note here, that's a plus. Plus implies discharge. And what do I mean by discharge? What this tells us here is that it discharges by 1 volt. And you know what? I'm going to come back and I'm going to erase and add one more thing. And what I'm going to do here is that I'm really going to do, this is 1 times e to the minus 2.5 t. Sorry for that. Because note that 1 tells me that it discharges by 1 volt. So that means it's going from a higher initial value to a lower final value. So if I go and I plot this thing, what am I actually seeing here? What I'm seeing here is that at VC of 0 plus, I see that this is 2 plus 1 times e to the minus 0, which then gives me 3 volts. So of course the initial value is that, right? This is our initial value here. And then VOC, which in this case is 2 volts, is our final value. So when I go and I do the plotting now, so I want to plot VC of t for all time. So then when I look at this curve, what does this curve actually look like? Well, you can see that I'm coming in at 3 volts, right? So here I come. I come in at 3 volts, and this is VC of 0 minus at 3 volts. And now it's going to discharge. But what is it discharging to? It's going to discharge to VOC equal to 2 volt line. So then this curve is doing this thing here. And you could see here that this equation then reads 2 plus e to the minus 2.5 t. So that's exactly what we're seeing. So you're seeing that when I look at the solution, it must look like that. Now, another thing that we should really look at here is that it's characteristic that the capacitors current has a discontinuity. So what do I mean by that? It's characteristic that these two are not the same. Okay? They are not the same. So what do we know here? Well, so what I really need, I know that so what we say here is that at t equal to 0 minus, we clearly have an open. So IC of 0 minus is clearly 0. Look at the circuit, right? At 0 minus, this thing's an open. Of course, the current of the capacitor is 0. But as soon as the switch is thrown, that is not the case. But at t equal to 0 plus, IC of t is equal to C dV dt. So let's go calculate that. So if I do that, we could see here is that IC of t is then going to be the capacitor value, which is 0.05. And then I'm going to take the derivative of the solution of the capacitor, which is going to be 2 plus e to the minus 2.5t. And then, of course, I'm going to set t equal to 0 plus at the end. So when I look at this thing here, you're going to see that I have a constant here. So I'm going to get 0.05. And then the first term is 0, but then I'm going to get minus 2.5. That's the derivative. And then I'm going to set that e to the 0. So when you compute that, you could see here that the number that I'm getting here is a negative value. And this thing is going to read minus, let's see here. I think what I'm going to do here is that I'm going to make this a milli. So I'm going to go 1, 2, 3. So I'm going to get 50 times 2.5. That should be 125, right? 125 milliamps. And this guy is IC of 0 plus. So what I'm seeing here is that if I look at now IC of 0 minus should not be equal in general to IC of 0 plus. In this case, it tells us that 0 is not equal to 125 milliamps. So that's characteristic right there, right? So you should expect that discontinuity. So that tells me that the moment the switch of the cap is is thrown, that capacitor current is way different than what it was initially. And that's a very, very, very standard thing here. So now let's go look at the next circuit here. And so what we're going to do here is that I'm going to come in and I'm going to look at the second circuit. So this second circuit is more involved. Okay. This is definitely more involved. So let's go look at this circuit here. So what we want to do here is check out what I'm asking you to do here. So the first thing that we want to do is that we need to really kind of start thinking about this thing physically. So in A, what I want you to do here is that I want you to see first what you expect from your solution. Right? In other words, know your answer before calculating. Okay? And let me tell you why this is such an important piece. The reason why this is important is imagine the following thing, that some of these problems may take you several hours to do. So imagine that you solve a problem and you just spent 2 to 3 hours doing it, and then you find out you did it wrong. Isn't it more important to kind of know where you're going beforehand? And so what we want to ask here is this: does the cap charge up or discharge at t equal to 0 plus? Is it going to be increasing in voltage, or is it going to be doing that? Now let's think about this. So the first thing that you want to do here is that let's look at, so what we want to do here is that what does the switch do to the cap? Okay, what does it do to the cap? And so what we want to do here is that let's look at the switch. What does the switch do? So you could imagine that what happens here is that look at that 4 milliamp source. So the 4 milliamp source is doing what? It's coming in here. And what I'm going to assume here is that I'm going to come in here and I'm going to put a ground right here. So if this is the ground, it's very, very, very likely, but I'm not certain yet. My guess is that this source, 4-volt source here, is going to be active. So what I'm seeing here is that I'm seeing what's feeding the capacitor is a 4 milliamp source and a 4-volt source. So my guess here, remember it's a guess, and this is how you start to build intuition. And what my guess is saying here is that if this is the case, then I have two sources feeding the capacitor. And if I have two sources feeding the capacitor, then I'm going to charge it. So here's my guess, is that I have two sources charging up the cap. When the switch is thrown, this tells me here is that I kill off the 4-volt source. So if I kill off the 4-volt source, the cap is seeing less current flowing to it from the 4-volt source here. So what I'm thinking here is that because of this, I would think, so then my guess here is that I expect the cap to discharge. So that's a really important understanding here, because if you're going through your solution early on, what you should find here is that if it's not discharging, all your spider senses should be going off telling you, oh, dude, something's wrong. Let me go back and look. Don't go and spend 2 or 3 hours on a problem and then find out that you did it wrong. Use your intuition now to try to figure out what's going on. And so now what you're seeing here is that our whole goal here is to go in and calculate what? We want to calculate the current through that 2K ohm resistor.
Carlos, I'm trying to imagine what the charge or voltage on the capacitor might be, given that if you agree, the current must be going back across the 4-volt source to ground.
Well, I don't know if that's happening.
Well, where else is it going? I mean, what's the initial steady state of the...
Well, you're talking about when the switch is thrown?
No, before the switch is thrown, I mean, the 4 milliamps has to be going across the 4 volt source to ground. There's nowhere else for it to go.
Well, that may be true.
What do you mean?
I mean, I haven't calculated it yet.
You don't need to calculate. Look at the right-hand part of the circuit. Where else could it go? The switch is open.
Well, if it's in steady state, then I agree.
Yeah, it's not going across the cap. It has to be going across the 4 volts to ground. Does
but
that tell us something about the charge of the cap? I'm not picturing it right now, but
I think what you're asking though is you're asking too detailed of a question. You might as well get into the problem and solve it to answer that question. Because I think intuitively that's a very hard question to answer. I'm just saying, when you look at the circuit, can you guess what's actually most likely to happen?
Okay.
And that's all I'm saying. So then I want to go through the pieces now. So what we're seeing here is that our goal is to determine the current Ix, which is the current of a 2 ohm here. Okay, so that's what we want to do. So let's go through it. So the way we do this here is that the cap dominates the time behavior of the circuit. So we solve for the cap's voltage and then use it to determine Ix of t. Now, why do I do it this way? It turns out that it's more physical when you do it this way. You get to learn what's actually happening in the circuit. There is a mathematical way where we could just jump right into the differential equations, but man, we're going to have so much mathematics here. I'd rather ground you in intuition. So here I go. Step 1. I want to determine VC of 0 minus. Okay, so that's the first thing I want to do. So when you look at the circuit here, if it's open, you could see here is that I can combine the 4 and 2 on the left with the 12. So that gives me a 12 parallel to a 6, that's half. I divide 3 into the 12K, I get a 4K. So now I have a 4K here. This is going to be an open, and when you're looking at the circuit here, you could see, as Jason already said, you're going to look at this 4 milliamp that's going to be going all the way through the outside. So let's go redraw this circuit here. So after the switch is thrown, I combined this resistor right here. This is a 4K, but this is really a 12K parallel to a 4 plus a 2K. And that's how I get the 4K. Then I have a 2K. And then I have another 2K. And then my cap here is going to be open. And then I'm going to move this down a little bit because I have a current source that I got to put up there. So then I have my current source that's coming in. And this guy's a 4 milliamp. And this guy's going to connect over here. And then I have a 2K here. And then I have my 4 volt source here. And here I have 4 volts. This is 2K right here. So what I want to do here is that the first thing I want to do is that I want to think about my ground. So I'm going to come in here and I'm going to go, here's my ground. So if I look at my ground, you could, there's, you know, the question is, we want to solve for the voltage, the initial voltage of this cap. The question is, how do I know what's positive and what's negative here? Well, the first thing that I would note is that we can see right away that this guy right here has to be 4 volts. And if I look at this current here, you could see that this current is flowing into this node right here, this current source that is. So when I'm looking at this thing, you could see that the current is flowing here. It's going to flow like this. And of course, it's going to flow right in here. So I have 4 milliamps going here. I have 4 milliamps here. And when I'm looking at this guy here, this sets the polarity of this guy to be plus and minus like that. So in other words, this guy right here, the voltage of this 2K should then be 2K times 4 milli should give me 8 volts. So from the ground, you could see here that I'm going to get 4 plus another 8. That tells me that this node right here must be 12 volts. Now, I don't know whether that's the high of the cap or the low of the cap. So then I'm going to keep going along. And as I keep going along, look what this 4 amp in the ground is looking like. Here it comes right here. And what does that 4 milliamp sees? Well, it sees the 4K resistor, and then it sees two 2K resistors in series. So since I have 4K and 4K, that means it's going to split this guy evenly, where now I have 2 milliamps going up that 2K. But wait a minute, if I have 2 milliamps coming from the ground, then this node right here tells me that this purple node should be 2K times 2 milli gives me 4 volts. But if it's coming from the ground, it must be minus 4 volts. So in other words, when I look at the voltage of this cap here, I see now that this is 0 minus. So now computing this, what I'm seeing here is that the initial cap voltage is then going to be VC of 0 minus is going to be 12 volts minus 4, which then gives me plus 16 volts. Right? That gives me plus 16 volts. So now I have my initial voltage of the cap, and I could now go on to the second step here. So second step, switch gets thrown. So if the switch gets thrown here, remember what it does, it shorts out the 2K and the 4 volt source here. So if I come back and look, you can see that this whole branch is now gone. So I replaced this whole thing with a short here. So here we go, step 2. So now at t equal to 0, I now determine the Thevenin parameters. And what are those parameters? VOC, RTH, 1 over tau. So let's write out the circuit here. So this is what I'm looking at. I have a 4K. I have a 2K. I have my current source here, which is 4 milliamps. And then I have my 2K right here. And then I have my cap here. This is what my circuit is right here. And we've already seen that this guy has a polarity that starts off positive like this here. So now this is what I want to solve for. But remember, we also want this current I of X going down. So let's get started. So when I do this, first thing I'm going to do here is that I'm going to do what? I'm going to open the current source. Oh no, sorry about that. I'm going to remove the cap and then solve the problem. So I'm going to determine VOC first. So if I do that, I now remove cap. So then my circuit looks like this here. It actually looks very similar to our previous circuit. Here's a 4K, 2K, 2K, and then I have my current source. I think I'm going to leave it like this. And according to what we've been seeing, I'm going to call that VOC. That's what I want to do. Again, this is fairly straightforward because with that short, that makes our life a lot easier. Why? Because I'm going to put the ground right here. Again, what am I seeing? Look at the current. What is the current doing? I have 4 milliamps here. So I have 4 milliamps here. So that means I'm going to get 2 milliamps here. And then going up, I'm going to get 2 milliamps here. So you could see here is that now I can see that this node right here is, of course, 0 volts. And then when I look at this guy, I'm going to get up to that same node. We've already shown this node, and it's as before. This guy is going to be equal to minus 4 volts. So when I go calculate VOC, you're going to see here that I'm going to get 0 minus 4. So I'm going to get 4 volts. So what was our guess? VOC started at what? 16 volts. This is now dropping down to 4 volts. So our initial guess here, so our initial guess was a discharging cap. So what does this mean? What this means here is that all of a sudden we're finding that VC of 0 minus, which is 16 volts, is now greater than VOC, which is 4 volts, and that indicates discharging. So that was a good guess. And again, it's just practice. It's not magic. It's just practice more than anything. So now what am I going to do? I'm going to go determine RTH. So what do? I open the current source. So here I go. So if I open the current source, what that means here is that I have the following thing. Well, I have my 4K here. I have my 2K here. And then, of course, I have my open right here. And then I have my 2K here. But now my current source is open like this here. So what this really means here, maybe I should have drawn this a little bit different just to make sure that things are a little bit more clear. All we care about is we care about this Thevenin resistance through this thing here.
Carlos?
Yeah.
Would it be more thorough to say VOC 0 plus? I mean, because you could really technically do that at either state. You know where you...
Wait a second. Didn't I say that up here? Step 2 at 0 plus?
Yeah, I mean, we've established that it's at 0 plus. I just, down here where you say VC 0 minus, if you're going to bother to put it in there, why not put VOC in? I guess, it would be a little redundant, but it would...
Yeah, I think it is redundant, right? I think we've already defined that when we go calculate voltages, we're using this relationship. VOC immediately implies 0 plus. It never implies 0 minus. That's why it says right here, this is before the switch. And then here, then it says after the switch. I think we defined that pretty clearly already.
Okay, so your concern with them being not only is it redundant, but it's actually potentially confusing because VOC is always at 0 plus.
I would just say go read what the strategies have been said.
Gotcha.
So then if I look at this, you know, just to make simplify the circuit a little bit better, it really looks like this. If this is easier for you to see here. So now we're looking at this RTH here. And this wire here can be a little bit tricky here. So let me help you with this one. So if I look at the current, you could see that the current is splitting here. So what you're seeing here is that you're really seeing a 6 ohm, 4 plus 2, in parallel with the 2. So when I would call RTH then, RTH is really a 4 plus 2 parallel with the 2. And if you look at this, this is going to be 6 divided. So 2 is a third of this. So it's got to be 6 divided by 4K, which will then be 3/2 kilo ohm for RTH. So now I got my RTH value. So now I got to go determine 1 over RT, 1 over tau. So now I'm going to go determine 1 over tau. So if I look at my cap value, it's 100 microfarad. So then that means that the way I typically, before I was actually putting numbers together, but I'm now going to just go right after 1 over tau. So that means that's RTH times C. So then this would be, well, 1 over R is then going to be 2/3 K. And then the cap here, which is 100 micro. And if you compute this, this will be, typically I'd start dealing with powers of 10 right away. And what you'll find out here is that this is 20 over 3 hertz. So this is 1 over tau. And so now I have that value. Now what I'm going to do here is that I'm going to go put it into solution form. Okay, so let's go do that. So when I do that, I'm now on step 3. So now I'm going to put into solution form. So if I do that, we already know what the solution is of this guy. And there's a couple of ways of actually writing this thing here. For the sake of simplicity, I'm going to write it in a more redundant form, just to be really clear. So we know that this must be VOC plus VC of 0 minus VOC e to the minus t over tau. So then I put this in, this is going to be 4 plus 16 minus 4 e to the minus 20t over 3. So I could write the solution for this guy as 4 plus 12 e to the minus 20t over 3 volt. So I could totally say this is my voltage of the capacitor for all time. But I'm really interested in trying to, you know, sort of like interpret this thing here. So if I now go and I try to interpret it, what am I really seeing? Well, at VC of 0, this guy's going to be 4 plus 12 e to the 0, which immediately tells us what the voltage was before and after the switch, which is 16 volts. And then what I'm seeing here is that when I look at VC of t, what you're getting here is that you're getting 4 plus 12 e to the minus 20t. And what I want you to pay attention is this guy right here. This guy tells us that the cap has discharged by 12 volts. So if I go and I plot this thing, what I'm really seeing here is that I'm seeing this type of thing. I'm coming in initially at what? I'm coming in at VC of 0 minus at 16 volts. And then this guy's then going to discharge to VOC, which is now 4 volts. And you're seeing this big jump here. So when I'm plotting VC of t, you're seeing that there's a big jump from here to here. That voltage jump is 12 volts. That's what that solution means. Okay, so let's keep looking at this thing. However, we got to get to the problem.
Carlos?
Yeah.
Question. So kind of going back to what Jason was talking about, when we talk about VOC, is that somewhat synonymous with infinity when the capacitor's at
That's
steady state after the
exactly-
switch is thrown?
That is exactly what it is. And
Okay.
And if I come into here and we go back to a previous lecture, look how I interpreted this thing here. See, VOC is V final state.
Right.
That's what I was trying to stress last time. That's what I mean by the final steady state.
Got it. Thank you.
So now if I come back here, what you're seeing here is that now, guess what? We have to solve the circuit problem. And in this here, we need to calculate Ix of t.
Carlos, real
Let's
quick.
go look at that thing.
Carlos, just real quick. What
I can't, is somebody talking?
Yes. What was the frequency we found? Is it kilohertz or hertz?
Was it 20 over 3?
But is it hertz or kilohertz?
Let's look at that. It might be kilohertz. I think you're right. Because if you look at this thing, this should be what? This should be 2 over 300 times 10 to the negative 3. So then this guy is going to be 2,000 divided by 300. So it's, no, it's not kilohertz.
So it's hertz. Okay.
It is hertz.
Okay. Thanks, Earl.
Okay.
And just for a second, could you scroll up a touch higher so I can grab a screenshot?
Say that again.
Thanks.
Okay, so I'm going to go back down. So I need to solve the circuit problem. So when, of course, the circuit problem is when the switch has been thrown. So when I look at this thing, so this, when I say solve the circuit problem, we're always talking at t equals to 0 plus. So now I go back to my original circuit here. Here's my 4K. Here's my 2K. Here's my other 2K. Now I have my current source. And then I have my cap right here. So the only thing I know what I've done here is that I've calculated this VC of t. And what I'm interested in is that I'm interested in what I want this current Ix right there. So we can immediately see here is that when I look at this thing, this guy has a polarity of plus and minus. So what we're seeing here is that we're seeing that VC is parallel to the voltage across the 2 ohm, but with opposite polarity. So in other words, VC of t must be minus the voltage across the 2K of t, but this should be minus 2ix of t. So that means then I could then go in and I can solve for this guy here. So what do I know here? So I need, so the fact that this is a resistor, we got to be really careful. Resistors can have discontinuities. In RC circuits. So that means I got to go, so when I say Ix of t, I got to go get Ix of 0 minus, and then I got to go get Ix of t after the switch is thrown. So this is for t less than 0, and then this is for t greater than or equal to 0. So let's go look at this thing. So the first thing that I got to do is I got to go find what the initial value of that current is. So I got to go back up. So we actually calculated this thing in step 1. And you could see here that right here, what this is really telling me is that this is Ix of 0 minus. You know what I'm going to do? I'm not going to do that. I'm going to bring it down bring it down. I'm going to bring down.
Resistors can have discontinuities in RC circuits. Just current discontinuities, not
And
voltage.
voltages too.
And voltage too. Okay.
Yeah. So this is the switch here. Okay. This is what we're seeing here. And what you're seeing here is that when you look at this guy right here, right, what we're really interested in is we're interested in the initial voltage here, excuse me, the current. And what we're seeing here is that this current here is Ix of 0 minus. So in other words, what we're seeing here is that Ix of 0 minus must be minus 2 milliamps. So now I got the initial current of that resistor. So now what happens? What happens next here is that we're using this guy here to answer this question. So if I go and I look at this guy, what I'm seeing here is that now, though the current Ix of t is then going to be minus 1/2 the voltage of the cap at t. So then if I go in and I put in my value here, you could see here that the voltage of the cap, of course, is this guy right here, which I will bring down with us. Right, just to make sure that I don't make any mistakes. So if I look at this thing, this is really going to be minus 1/2 of 4 plus 12e to the minus 20t over 3. So if I compute this, this guy's going to be what? Minus 2 minus 6e to the minus 20t over 3. And this is going to be in units of milliamps, is what I should be seeing. So I now know what these guys are. And so what I want to do here is that instead of sort of like separating like this, I want to write them out so that we're nice and clear. So now what we have here is that the complete response of Ix of t then should look like this. Well, I have minus 2 milliamps, and this is for t less than 0. And then I have minus 2 minus 6 e to the minus 20t over 3 milliamps. And this is what Ix of t is. So now let's go plot this thing. So if I plot this guy, what am I seeing here? Remember, we expect discontinuities. That doesn't mean that there's no discontinuities, but we expect discontinuities. So when I go and I plot this guy, what am I seeing here? Well, I see that this guy is doing what? Here's Ix of t. We're coming in at some value, and I see Ix of 0 minus should be minus 2 milliamps. Now, what I'm seeing here is that at Ix of 0 plus, I'm going to get minus 2 minus 6 e to the 0, so I'm going to get 8 milliamps. So what does that mean? I'm going to get a jump here, right? There's a discontinuity, and it's going to jump all the way down to here. And then what you're seeing here is that I have this line like this here, and then there's this jump where it jumps all the way down to what? Minus 8 milliamps, and then it jumps all the way back to here. Right? It's going from a more negative value to a more less negative value. So there's an, I guess we could say that there's an increase in current. And then this solution here is then minus 2 minus 6 e to the minus 20t over 3 milliamps. And that's what that plot is looking like right there. Okay. So, another thing that I think we should just leave it right there. So, maybe we should say a couple of things. So another thing that we should look at is that when does the resistor reach steady state? And the answer to this, it reaches steady state when t is equal to 5 tau. So when t is equal to 5 tau, what is that value? Well, I know that this is 5, and let's go look at what our tau value was. So I'm going to copy that down here. So if I look at this guy, here's what our tau value is. So if I bring this guy down, you're going to see that this is our tau value right here. So if I look at our tau value, what am I seeing here? What I'm seeing here is that this really is what? 3 over 20. So this is going to be 15 over 20, which then gives us, of course, what? What is it? That's 3/4 of a second. So this is going to give me 0.75 seconds. So at 0.5, I'm going to say here is that Ix of t equal to 5 tau, this should approximately equal minus 2 milliamps. So when it reaches this line, we could come in here and just say, okay, this is 5 tau, and it's roughly at 2 milliseconds right there. Okay, that being said, I think we should move on. We want to go in and start looking at the RC circuit. I said RC, I meant RL. Now we're looking at the RL circuit. And what you're going to find with the RL circuit here is that it's very similar to the RC circuit. So what we're doing here is that what's different about RL is that we put it into a Norton circuit. Okay, we put it into a Norton circuit. So here we go. So you could imagine that I start with the exact same circuit that I started before. So I have a plus and a minus sign for my source. And then I had this circuit that looks like this. So remember, the type of circuit doesn't really matter. because we're always going to try to put it into a Norton circuit. And we're going to close this guy at t equal to 0. And our whole goal here is to figure out what is the current of this inductor right here. That's our whole goal. And what we're going to do here is that we then want to transform this circuit so that I have I short circuit, my Norton current source. I'm going to get my Norton resistance. Remember, the Norton resistance is the same as the Thevenin resistance. And now I have an inductor, L, and I want to convert that circuit so that I could then calculate this guy here. That's what my goal is. So once again, what we're going to find here is that we're going to have a very similar situation as before. So what we really call the solution to this thing here, so we could then say that in summary, because we already did this, there are two steady states and one transient state. And what I mean by that is that when I talk about the complete response of the inductor, what I'm saying here is that there's going to be some L of 0 minus. That's my initial steady state. And then I'm going to have my transient period. And what I mean by my transient period is that I'm looking for some time that's typically between 5 tau and 0. This is my transient period. This is exactly what happens right at 0 plus. And then eventually, this thing is going to go to its final steady state at t equal to infinity or 5 tau. And what you're seeing here is that at t equal to infinity, you could see that the inductor is going to act like a short. It's going to kill off the Norton resistance. So I short circuit and the current of the inductor will be the same. So this guy is our final steady state right here. So what you're seeing here is that in between the two steady states, I have this transient state that's sandwiched in between there. And as we talked about with the capacitor circuit, there are 4 circuits that you typically solve for. And you solve for, and you can see what the solution is. You're going to solve for what? You're going to get the initials. So you're going to get circuit number 1 here, because you got to solve for the initial value before the switch is thrown. Once the switch is thrown, you then need circuits 2 and 3. Why? Because you're going to need the Norton parameters. And the Norton parameters is going to be I short circuit, I Norton, and 1 over tau. Now I got that. And then, so the final steady state goes in like this. So then you're going to have a 4th circuit where now you have to solve the circuit problem. So it's very similar to the process of the cap. So now what we want to do here is that I'm sort of going to let the solution, I'm going to, let the solution pop out, just kind of write it here just so you could see it before we get there, but it shouldn't be a surprise because it should have the exact same form as the capacitor. And why is that? They have the same differential equation. And you're going to see here is that the solution is then going to be what? It's going to have I short circuit, IL initial minus I short circuit e to the minus t over tau, where this tau is now going to be different. And again, this is our force response, and then they call this the natural response. I really don't like this form, but it's the most useful mathematical. And the reason why I don't like this form, as I said before, is that when you get into a second order differential equation, this form changes. Most textbooks and most online people reinterpret this. I typically like to interpret it only one way, but that's okay. So what we're going to do here is that we're going to assume that we have all of this. That means you now have, so what I'm going to do here is that I'm going to assume we now have a Norton circuit. That means I calculated I short circuit, I calculated Rm, I calculated 1 over tau. And so here's what I find here. So now what I'm going to do here is that I'm going to now solve for the inductor current. So here's my circuit now. So I have a circuit that looks like this. I have a Norton resistance, and I have my inductor. And my whole goal is to calculate this current right here. So when you look at this thing, what you're finding is that these are all parallel elements. So if I try to use KVL to solve this, it doesn't make any sense. I must use KCL. Okay? But we should do this wisely here and say, let's choose this guy to be the ground. So now what we're seeing here is up here is, of course, the voltage of the inductor. So now what we're going to do here is that we're going to apply KCL to one of those nodes to actually solve for this thing. So here we go. So now we're going to apply KCL, and we immediately see here is that the current going in, of course, should have a current coming down like this here. So if I'm looking at this, KCL tells me that I short circuit should be the current of the Norton resistance plus the inductor current. Now, if I look at this thing, I need to convert this into a differential equation. So the way I'm going to do this, I'm going to say is that the current of the Thevenin resistance then should be VL over Rn plus IL of t, but I know that VL is L di dt. So if I bring this into the equation here, it's going to look like what? I'm going to get here that this equation then tells me that it's going to be what? I'm going to get dIL dt, and then I'm going to divide this by the parameter RL, I'm sorry, I should have said Rn divided by L plus the inductor current, and this guy's going to be I short circuit. And so the common thing to do here is to isolate di dt. Okay, so I'm going to isolate dIL dt, and if I do that, I write this equation. And I'm going to, by doing this, I'm going to then divide both sides by this here, and then I'm going to get, oops, not an equal sign, it's a plus sign. It's going to be IL divided by the quantity L over RTH, sorry, Rn equals I short circuit L over Rn. This is my first order circuit. So this is the first order equation for a Norton RL circuit. So we should use some common notation here so that we could see what we did before here is that I'm going to set x equal to IL. I'm going to set tau equal to L over RTH. And then I'm going to set K equal to I short circuit divided by tau. So if I do that, then I'm going to get a solution that looks something like this here. I'm going to get dx dt plus x over tau equals k over tau. And you remember that we did this with the capacitor equation. So this tells us that the solution looks like what? It looks like x of t, x of 0 minus, plus, oh, that's not what I should have written. It should be infinity. And this will be x of 0 minus minus x of infinity times the quantity e t over tau. So if I then translate this into the inductor equation here, we find then that the complete response of the inductor current to a constant source is then going to be IL of t, I short circuit, plus IL of 0 minus, I short circuit, e to the minus t over tau.
Carlos, in the where it says set blah blah blah, is it supposed to be T equals L over R Norton?
But I can't hear what you're saying.
Where it says set tau equals L over R Thevenin is supposed to be R Norton.
Yeah, you know what? I'm going to have trouble with that, but note that those two resistances are the same.
Cool.
So if I write Thevenin or if I write Norton, they're really the same. So I'll try to write Norton, but I'm probably going to screw up because we've primarily been dealing with the Thevenin resistance. So what I want to do here is that I want to go back and I want to briefly remind you what we did beforehand. Okay. And so what I want to do here is that I want to look at this guy and I really want to pay attention to only one thing and one thing only. So what I want to do here is that I want to sort of like do a brief physical interpretation of the solution. And the reason why I want to do this here is that I want to remind you that it has the same physical behavior, but it has also the same mathematical behavior. So the first thing that I want to do here, and I want to ask, how does the solution tell you when current is being stored up? And it's very common for people to say, oh, you're charging up an inductor. Well, let me tell you about the inductor. The inductor has a net charge of 0. So that's a meaningless statement. So it's either storing current or decaying current. So that's why I use the word stored up. It's storing current when it's going to a higher value. So mathematically, what does this look like? So mathematically, this says that IL of 0 minus must be less than I of infinity. Oops, I want to get that L in there. But that's I short circuit. Okay, so I short circuit is bigger than that. So when I look at the solution here, what I'm going to do here is that I'm going to define di as the absolute value of IL of 0 plus minus I short circuit. So if I do that, we can see that this quantity here must be negative. So when I look at this thing here, what we're seeing here is that mathematically what it looks like is that I'm going to get a value that reads I short circuit, and then I'm going to get delta I e to the minus t over tau, but I see a minus sign right here. So as we saw with the capacitor, this minus sign implies storing up current. Okay, it's storing up current. So when I look at that solution here, it's going to look something like this here. So that means that that IL of t versus t, that means I'm going to come into some value here, which will be I short circuit, and this guy's coming in at IL of 0 minus, which is going to be less. And then as soon as the switch is thrown, you're seeing that this guy is going to store up to I short circuit. And so when you look at the jump in the current, that jump in the current from here to here is explicitly this value of delta I, which is the magnitude of IL of 0 minus I short circuit. That minus sign is telling you that it's going to go to a higher current and therefore storing. If I do the same thing for the decay here, so when current is decaying, then what we're seeing here is that IL of 0 minus is greater than I short circuit. So what this tells us here is that the solution IL of t, which starts off at, of course, I short circuit here, when I look at that delta I thing, you're going to get a plus sign right here. And that plus sign tells me what? The plus sign implies decaying current, right? It's a decaying current. So when I go and I look at this thing mathematically here, what we're seeing here is that I now have an initial current coming in. So I have my current coming in, and this is IL of 0 minus, and then this guy is going to decay to a lower value. And when it decays to a lower value, we already know that this value right here is I short circuit that is going to decay to this. So when I look at this guy's going to drop down to this value right here. And then once again, what are we seeing here? We're seeing that this drop is given by that cofactor of the exponential, which is delta I. So that's what that plus sign means here. So we only have a few minutes, but what we should be looking at is this guy right in here. We should now be looking at this example right here. And you could see I'm doing a lot of examples. I'm trying to beat into you what is physically happening in these circuits here, because this is essentially the last circuit that you have to build intuition for what's happening here. You're going to see that the rest of the circuits, I'm going to complicate things by a source, where now we're going to deal with step functions. And how do you write down a step function mathematically that makes sense? And then that's it. Then we get into the time-dependent sources here. And then we radically change how we solve these things. But before we go, look at this circuit here. And I want you to try to take the same type of thinking that I did previously and tell me, is the current of the inductor increasing or storing current, or is it decreasing, decaying current when the switches are thrown? What would you think here? Just look at that thing and tell me what you think.
I have a guess, but I'd let any student venture first.
I would say decaying current, only because that current source on the right is going to be shorted out. And so that current's no longer going to be going to the inductor.
Okay, so look at the value of that current source on the right. It's 500 milliamps. Okay. And then you're right, when this gets shorted, then I now turn on the 100 volt source here. So when I turn on that 100 source volt, because they're not on simultaneously. So the question is, does the 100 volt source deliver more current to the inductor, or does the 0.5 amp source deliver more current to the inductor?
Is there any way to know that without actually solving the circuit?
No, it's just, you definitely have to solve the circuit here. But,
Right.
but let's think about this here, but just for a brief moment, because I got to get the hell out of here. Look at that 100 volt source here. When that switch is thrown, this piece is gone. So when I look at that 100 volt source here, it's going to, well, that thing's going to go to a short. So all of a sudden, I'm dividing that 100 volts across the 600 versus the 400. So I'm going to see a smaller voltage here, right? So I would think that it would be decaying because of the sharing of the voltage. I think we should stop here just because I'm already 1 minute over. So I got to get the rest of those oscilloscopes out. Okay, and I'll send an announcement with the links that I have for the software and when I'll be at Cabrillo, so that I can try to get those out as quickly as possible. Okay, I'll talk to you guys later. So look for that announcement sometime after 12:30 today. Okay, I'll see you guys later.